Welcome to This Explainer. Today, we're going to methodically break down the mathematical foundations of linear regression. We're bridging that rigorous world of classical econometrics right into the fast-paced, highly practical world of modern machine learning. Whether you're actively building predictive models or you just really want to understand the exact engine running under the hood of most statistical software, this step-by-step journey is for you. Let's kick things off with a pretty fundamental question. How do we actually mathematically capture complex relationships in data? As machine learners, our ultimate goal is often to approximate these unknown underlying truths of the universe using literally nothing but the small samples we manage to observe. So today is a guided discovery of exactly how we build those mathematical approximations from the ground up. Here's our roadmap for today. 1, the intuition behind linear regression. 2, the method of least squares. 3, the Gauss-Markov theorem. 4, checking model adequacy, and finally, 5, modern solutions and regularization. All right, let's dive into part 1, intuition behind linear regression, bridging theory and data. Before we even touch a matrix or a single summation symbol, we need a mental anchor. Imagine you've got a fresh data set in front of you. We have to understand the core difference between two types of models. Mechanistic models? Well, those are built on known physical or scientific laws. But in most real-world machine learning applications, we just don't know the true underlying mechanism. That's exactly where empirical models come in. Linear regression is an empirical model. It's a data-based approximation we use when we don't know the exact rules governing the system, but we need a highly effective guess. Think about the true relationship in your data. It might be this wildly complex, unknowable curve. But it's actually amazing how we can use a piecewise linear regression function to approximate it really well over specific intervals. Even when the real world is nonlinear and messy, drawing straight lines through the data gives us a surprisingly powerful, workable empirical model. But there is a huge catch here. This empirical approach has severe limits. Our regression equations are generally only valid over the observed region, the data we actually collected. Trying to predict values outside of this specific range is called extrapolation. And the moment we move beyond our observed data points, our straight line can completely miss the true curve. Basically, extrapolation is a highly dangerous mathematical endeavor. Moving on to part 2, the method of least squares, or how we actually fit the model to the data. Okay, now that our intuition is totally grounded, let's formalize this. We need to define the exact cost function we're trying to optimize, and we do this using the method of least squares. We estimate our parameters, beta 0 and beta 1, by minimizing the differences between the actual observations and our predicted line. We take those vertical distances and we square them. This is crucial because it ensures negative and positive errors don't just cancel each other out, and it heavily penalizes the larger errors. Then we just add them all up. And to actually find the absolute minimum of that cost function, we just do a bit of patient calculus. We differentiate it with respect to our parameters and set those derivatives straight to 0. This yields the normal equations, which are remarkably easy to solve. The result is an exact, closed-form equation for our regression slope. It's a beautifully deterministic way to find the absolute best-fitting line through our sample data. Which brings us to part 3, the Gauss-Markov theorem, the absolute cornerstone of econometrics. So how does this least squares math actually translate into solid theoretical guarantees? Well, the Gauss-Markov theorem is the gold standard here. It justifies exactly why we love ordinary least squares, or OLS. It mathematically proves that under specific conditions, OLS produces the best linear unbiased estimators, famously known by the acronym BLUE. Unbiased just means that, on average, our estimates hit the true population parameter. And best means that out of every possible linear unbiased estimator out there, OLS has the lowest possible variance. It's the most precise. But, and this is a massive but, this beautiful theory only works if your data strictly plays by the rules. The relationship must actually be linear. The errors have to have a mean of 0. We also need homoscedasticity. It's a huge word, but it literally just means the variance, or the spread of our errors, stays constant across all our data points. Plus, the errors can't be correlated with each other. And while normality isn't strictly required to be blue, we definitely need normally distributed errors if we want to run reliable hypothesis tests. Okay, part 4, checking model adequacy. What happens when those assumptions fail? Because let's face it, in the messy real world, theoretical guarantees break down all the time. Building a model is almost never a one-and-done kind of deal. It's fundamentally an iterative procedure. We use our domain knowledge, we specify an initial model, and we estimate the parameters. Then, crucially, we have to check its adequacy, usually by plotting the residuals. If we find out our assumptions are violated, we modify the model and start the whole loop over again. During this iterative loop, we are actively hunting down the villains of regression. We're scanning our residual plots for nonlinearity or heteroscedasticity. We're also keeping a very close eye out for multicollinearity. That happens when our independent variables are highly correlated with one another. When your features basically contain the exact same information, your data becomes ill-conditioned, and that makes our OLS estimates highly unstable, wildly fluctuating, and honestly, totally misleading. Luckily, we've got some mathematical tricks up our sleeve to defeat these issues. Take data transformations, for example. Say we have a nonlinear model with a multiplicative error structure. Well, simply taking the natural logarithm of both sides can transform it into an equivalent linear form where the errors are additive. By transforming the data, we mathematically induce linearity, which lets us safely go back to using our standard OLS machinery. Finally, Part 5, Modern Solutions and Regularization, specifically focusing on shrinkage methods. Because, simple transformations aren't always going to cut it, especially for machine learners dealing with massive data sets packed with thousands of features. Remember how the Gauss-Markov theorem praised OLS for being unbiased? Well, in modern machine learning, being perfectly unbiased isn't always the ultimate goal. Standard OLS can be incredibly unstable with high-dimensional data, so shrinkage methods deliberately sacrifice that unbiased nature of OLS. By intentionally introducing just a tiny bit of controlled bias, we can massively stabilize our models, lower the overall variance, and significantly boost our out-of-sample prediction accuracy. A fantastic example of this is Tikhonov regularization, which you probably know as ridge regression. Honestly, think of ridge regression as a mathematical shock absorber. It tweaks our least squares cost function by adding a penalty term for large coefficients. By forcefully shrinking those coefficients closer to zero, ridge regression rescues our model from the numerical chaos caused by multicollinearity. But ridge isn't the only game in town. We've also got lasso. While ridge shrinks coefficients continuously, meaning it makes them smaller but rarely hits absolute zero, lasso uses a slightly different mathematical penalty. It takes things a step further by forcing some of those coefficients to become exactly zero. And that's incredibly powerful because it performs automatic feature selection. It simply drops the useless variables, leaving you with a much cleaner, highly interpretable model. So I want to leave you with this provocative thought to chew on. Could the pursuit of a perfect fit on your training data actually be harming your model's true predictive power? As we've seen today, perfectly minimizing that classical least squares cost function can lead to highly unstable models that just completely fail in the real world. In machine learning, an unbiased, perfect fit is very often the enemy of generalization. Sometimes a little bit of constraint, a little bit of intentional bias is exactly what you need to discover the true signal hidden in the noise. Thanks for joining me on this explainer. Keep questioning, keep learning, and I'll